All right, we are on Unit 5 Progress Check Part A. We're doing number 5 here. So let f be a differentiable function. So all of f is differentiable, and you know a few values, f of 0 and f of 11, which of the following must be true for some c in the interval 0 to 10, the open interval 0 to 10. However, we do know that it's differentiable along this whole thing as well and continuous, because if it's differentiable, it's also continuous. So part A, so it just gives us different things here. Choice A says the derivative is 0 since the extreme value theorem applies. Well, the extreme value theorem has nothing to do with derivatives, so that is not it. Part B, the derivative of C equals 11 plus negative 4 over 10 minus 0. Since the mean value theorem applies, that could be true. So let's look into this. We have the slope. So the slope, the mean value theorem says if it's a closed interval, if it's continuous and differentiable, then if you find the slope of the line connecting the endpoints, so that's what we'll do. We'll do 11, so that's our y value, minus negative 4, which is our other y value, over 10, our x value, minus 0. So that is not correct because that's not the correct slope. So it's not this one. So it's probably C here. Which the following must be true for some c? Well, there should be a derivative of c that equals the slope, and so it's that one. Down here, number 10 doesn't work because the intermediate value theorem doesn't have to do with the derivative either, so it's not that one. So the answer is C. Moving on to number 6. Let f be the function given by f of x equals x plus 4 over x minus 1 times x plus 3 on the closed interval negative 1 to 5, on which of the following closed intervals is the function f guaranteed by the extreme value theorem. So extreme value theorem, it has to be continuous on the closed interval. All right, to have an absolute maximum and an absolute minimum. So like before, we know this is a rational function. We know that at negative 3 and 1, those are not part of the domain, so we need closed intervals. So we need something that won't cross over that. Well, if you go from negative 5 to 5, you can't use the extreme value theorem because there's undefined values at negative 3 and 1. From negative 3 to 1 with the closed interval, you can't do that either because you can't use negative 3 and 1. If that was open, well, extreme value needs to be closed, but this is these negative 3, both negative 3 and 1 are undefined there. Negative 2 to 0, negative 2 to 0 goes from here to about here. That one is okay. So C is probably our answer. We can check 0 to 5. 0 to 5 would cross over this spot that there's an undefined value. So it's not D. Number 7, let f be a function defined by f of x equals x times sine of x. With a domain 0 to infinity, the function has no absolute minimum and no absolute maximum on its domain. Why does this not contradict the extreme value theorem? Extreme value theorem needs to be continuous, which it is. X times sine of x is continuous, and it needs to be a closed interval. So domain is not open. That's not correct. We don't want it to be open. The domain of f is not closed and bounded interval. That looks like it's our correct answer. This one says it's not continuous. It is continuous. This one says it's not differentiable. It is differentiable. So our answer definitely is B. Number 8, selected values of a continuous function. So that's important. Continuous, it doesn't say differentiable. So it's a continuous function are given in the table above. Which of the statements could be false? All right, hopefully we're learning that knowing continuous and not necessarily differentiable is important. Intermediate value theorem just needs continuous. Mean value theorem needs continuous and differentiable. So this one could be false. The extreme value theorem just needs continuous. Extreme value theorem just needs continuous. We don't need to look into any of the details there because the only one that can't be used, or we know the mean value theorem can't be used because it never said it was differentiable.